YouTuberverse. Tyson here, StarTalk next. Summer school is in session. This is StarTalk. I'm your host, Neil deGrasse Tyson, your personal astrophysicist, and we're coming to you from my office at the Hayden Planetarium of the American Museum of Natural History, right here in New York City. And this edition of StarTalk, we're calling Summer School.
Yeah.
Who said yeah?
The professor.
Friend and colleague, Charles Liu. Charles, welcome.
Thank you so much for having me. I love summer school.
You love summer school.
Absolutely.
And I got my co-host for this episode, Matt Kirshen. Matt.
Hey.
Welcome back.
Thank you so much.
All right. Host of probably maybe science.
Probably science.
Well, could be science.
Nearly science.
Not sure if it's science.
Almost there.
Almost there.
I can't believe it's not science. I know it's science.
Probably science. A weekly review of science current events.
That's exactly it.
Excellent.
That's the podcast.
Keep that going. Keep that going. Charles, professor?
Yes.
At the City University of New York.
So we're kind of equals here.
Absolutely.
Exactly.
No,
So
we are.
So this
peas
is
in a pod.
This is a Cosmic Queries version, but it's called Summer School. People just trying to catch up.
That's right.
With stuff they might have missed.
Or get ahead.
Or get ahead. I forgot. Summer school's for getting ahead,
that's
too.
right. Mm-hmm.
Right.
For motivated students.
That's right.
And with that in mind, I think let's start off with a quite an academically advanced question.
Let's do it.
Cooper Holland on Instagram asks, how hard would I have to fart to knock Earth into escape velocity? Also, wouldn't sunrise be a good time to try it? That's Cooper Holland from Arizona State.
From ASU, huh?
I'm coughing because I'm imagining how much gas needs to be used to make that happen. But the reality is, first, I assume you have an escape velocity from the sun, right?
No, he wants to escape from the Earth.
Oh, he wants to escape from the Earth. I thought he wanted the Earth to escape from the sun.
Oh,
now that
yes,
is
that's
a
different.
massive.
Yeah, it
That's
says
way
to knock
harder.
Earth into escape velocity.
That's harder than just if he wanted to
Right,
escape.
right.
Yeah.
If he can escape, that's easy.
Just a few cans of beans.
There you go.
We
Put
did
them on
it
a
twice
gantry.
this morning.
No, Earth would be a lot harder because Earth's orbital velocity is
I just
about,
now can't get that picture out of my head. He's positioned on a gantry
Yeah.
at Cape Canaveral.
Yeah, 3.
Last two cup of beans.
1.
They go,
Launch aborted for weather.
ascends
But is
into
that
orbit.
solid fuel or liquid fuel rocket? Huh?
Oh, yeah. No,
Yeah,
that
see?
would be.
See?
No, that's just air pressure
That's
fuel.
just
That's just pressure fuel.
So it's really a bottle
It's a
rocket.
pneumatic rocket.
Bottle rocket. Pneumatic rocket.
Pneumatic.
Or like the CO2 pellet.
Right,
Yeah.
right.
rifle.
Like
it's pneumatic.
Yeah. Wow. No, see, Earth's orbital velocity is about 30 kilometers per second.
Per second,
right?
correct.
Around the sun. You have to take the square root of 2 of that. And so that makes 1.4 times 30 is about 42 kilometers per second. Earth's mass is about 6.
Because it's a cute little fact that whatever is your orbital velocity around what you're orbiting, if you multiply that by the square root of 2, that's the speed to escape that object.
Yeah.
It's a very cool fact.
It is. It's neat. It's nice coincidence in math. And the Earth's mass, of
Square root
course,
of 2 is about 1.4. Yeah.
Yeah. Earth's mass is 6 billion trillion tons, right? So to generate the amount of impulse necessary to get Earth that much mass up to that velocity, that's a lot of cans of beans.
Yeah, because it's a momentum thing. So you need enough expelled gas so that the recoil of your planet can be meaningful and significant.
Right, and correct me if I'm wrong, but you'd also have to make sure you're in some way tethered to the Earth, so you're not just
You
blasting
can drag the Earth with you.
Right.
Otherwise, you will just fly off at a tangent. Right.
Yes.
Right.
So I think
Ideally, you'd want to get all humans involved in this.
Right.
you'd need.
You don't want to be holding
every-
onto a tree or something.
You'd also need every cow in the world.
Yeah, the cows.
You got to put them all together. I think that's a very good summer school problem calculation to do. Yes, Cooper, good luck with that. That's great.
But in principle, yes.
Yeah,
So
can
in
be
other
done.
words, if you are in space, there are various ways you can actually set yourself into motion. But to do so, you have to lose mass from your body,
Right.
either through gas, liquid, or solid.
Yep. And if you're at sunrise, that would be a good time because the best way to inject that extra velocity, the delta V, is in the direction of the orbit, the tangent to the orbit. So not straight out, as some people might think, but actually out at a 90-degree angle.
So you can build to the speed that the Earth has itself. Yes.
Right. Okay.
By the way, but all that methane, that could be a pretty dangerous situation.
It's true. One match. And
That's
you've
it.
Got, yeah.
Then you have a bomb.
That's a flare.
That's a bomb.
And also, that's a greenhouse gas.
Yes, it is.
Oh, yeah.
Yeah, very potent. More potent than CO2.
True. So you really have to light that thing. Yeah. So,
But then,
you would
lighting
fly out
it,
into
if
space.
you could control that
you could-
lighting,
No, wait
would
a
that
minute.
give
If
extra
would get-
thrust?
Wait, if you leave Earth,
Yeah.
you need the greenhouse gases
To
to
stay warm.
retain
There you go.
the warmth.
That's right.
Yeah.
So it's the balance. It's the balance. Yeah. Wow. That's very exciting. You know what? I think I'm going to have to assign that to my astrophysics class next year.
And then the dean will call you into the office and say,
Well, maybe Cooper will help me out with that.
Well, while we are doing calculations, Tom Foreman on Facebook asks, is math a discovery or an invention?
Beautiful, beautiful.
don't get me started. I want to hear Charles first.
Okay. Well, remember that my wife is a mathematician.
Yes, she is.
Right.
And my wife has a PhD in mathematical physics.
That's right.
Yeah.
Twinsies.
So we got math going in the
right.
family here.
Yeah. And my son also, given a choice of either studying math or astrophysics in college, has chosen math. Anyway, that's okay. We still love you.
Sorry.
Yeah, I know.
Such a disappointment.
When did you know? Were the signs always there?
When he was a little kid putting refrigerator magnets in strange shapes, I knew that something
Just
was
knew
up.
Something
was
he
up.
was hiding something.
Something
in
was
the closet.
up. Yeah,
Okay.
yeah. Anyway, math is something that exists by itself, but mathematics as we use it and formulate it today is an invention of humans. This is a clear reality of the universe, because things will do what they're doing whether we understand them or not. And we created math in order to try to understand and reproduce and utilize those things that nature provides for us. So, for example, when the ancients were building pyramids, they invented geometry, right? Those pyramids would have stood anyway if we had put them together and not known the equations. But with the equations, the ancients were able to build them properly. The same is true with, say, rocket equations that allow us to send things out into space. We could have sent things into space without knowing how to do the calculations, but we wouldn't have had much control over it. So, bottom line, the math you see in textbooks today or in papers, we humans have invented that following a set of rules that nature has provided for us as a template. Neil.
I'm okay with that.
Okay.
I'm okay. I don't like debates about whether one word or another word best describes it. I'd rather say that maybe our language needs yet a third word that perfectly accounts for it, and then we get rid of the argument altogether.
And would that word be a discovery or an invention?
It's the word between the two that we don't have.
Discovention.
It's why we argue.
Mathematics, math.
Is-
yeah, math.
Is it a particle
Discovention.
or is it a wave in quantum? Why are we arguing that? It's both. We just don't have a word. We tried wavicle, but it didn't catch on. A wave and a particle. So I just don't.
Sounds like some sort of branding exercise from the 80s. it's
70s, discovention, okay?
The fact that math works at all as a tool to decode the universe is evidence that the universe, at least the parts that have revealed itself to us, follows logical, repeatable patterns. And math is simply a way to code for logical, repeatable patterns. So it's remarkable that math can describe the universe at all, except that math is a perfectly logical system, and so is the universe. Put them together, of course. It's a marriage made in heaven.
Very much like music, right? Math, music, that kind of connection. And the Bee Gees understood that well with their song, Calculus, Calculus. yeah, Calculus.
And as I thought calculus was an emperor of Rome. That's an old joke. I heard that long ago.
I'm going to
Calculus, the brother of Clavius. Yes. Matt,
while we're talking about things
get us
between
off this
things,
topic really fast.
I will. Well, I'm going to combine two different questions together. So Eric Hansen on Facebook asks, I recently read that if all of the space were taken out of every human on Earth, the resulting mass would be about the size of a cube of sugar.
Yep.
How then can anyone adequately explain how the entire mass of the observable universe was once a point only microns wide? And then I'm going to combine this with this other question.
You're going to combine that?
That's a beautiful question
How
on its
are you
own.
going to add something to that?
Yeah.
Well, this is a little coda question. I could have thrown it out afterwards, but I thought I'm going to leave this just in your subconscious to bubble over while you're answering that one. From Ashton Norton, also on Facebook. Other than the Big Bang, are there any other scientific theories that have been discussed as possible explanations for where we came from?
Well,
so those two together or separate, as you choose.
Okay, so this is basically a cosmology question.
Sure.
Right? So I'll take the cosmology question number 1. You can take cosmology question number 2.
I like both of them.
All right.
No, I'm just kidding.
I'll answer each one
Go.
half.
Okay, you answer each half.
All right.
Leave me a little room at the end. Go.
All right. So the reason the universe is so different now than it was back then is simply because there was some kind of physics that happened between the moment of the Big Bang and the present day that we still don't yet understand. It is completely true that the universe back then, the density of the universe right around the moment of the Big Bang, at the Planck time we call it, was approximately 10 to the 97 kilograms per cubic meter. All right. And
that's pretty dense.
Yeah. And even if we took all of humanity... We're back in the 60s now. We went from the 70s to the 60s. We got to get some. Yeah, that's absolutely. You said it. We have a circumstance where the matter of that density is so removed from anything we can think of that human beings the size of a cube of sugar analogy, when you move all the space, that density is still only about 10 to the 15 kilograms per cubic meter.
So there was just another state of matter, or the matter itself was
Charles,
so different.
I thought it's not even that complicated. Okay. If it stays as solid matter, just taking out all the space between the particles, you're not going to get much smaller than that. But at the temperatures of the early universe, matter is not stable as solid matter. It's energy, and you can pack energy into any kind of small volume you want. So
that's the right way to say it.
Is that a fair way to?
It is a completely fair way to say it. And so as a result, the laws of physics that were governing that behavior produced something that eventually evolved into our universe today. And we have yet to decipher scientifically the processes that went from that to now. Wait,
I have to tighten that. It's not that it went from then to now. It went from then to a little bit after then. Because we know what happened a little bit after then until now.
That's fair.
That's good physics.
Yeah. And by little bit after, Neil, I think you're referring to 10 to the minus 30 seconds, right? Yeah. So 0.000000
a gazillionth of a second.
So we've managed to trace it back a very long way.
Yes. Right. But that last little bit,
that last gazillionth of a second is really hard to get. That's confusing bit.
And that segues into that second part of the question. It does. Where what is going on in that tiny, tiny fraction of a second that is so different from what we know today in our universe? And so that's where the speculation can lie, right? What could have happened other than a Big Bang as we understand it today? Could something else have generated the kinds of energies and effects that have led to the way the universe expands today? There's lots of speculation, but it's really, really hard to be able to decipher or to pinpoint the physics involved. We're adding extra dimensions, we're adding extra particles, we're adding all kinds of extra crazy ideas, and none of them have yet panned out in a scientifically verifiable way.
And let me just say, do you think we're happy about a Big Bang?
Yeah, that's a great point.
This is like weird stuff, all right? But evidence points to that.
Yeah.
The universe we now occupy can be described by what happens if you had a Big Bang as accounted for with a small, dense, hot, early beginning. And it gives us the amount of the hydrogen and helium and neutrinos and the age and the density and the distribution. All of this comes out of that. If you have a better idea, fine, we'll take it. But until then, we're stuck with the Big Bang. How's that? Is that another way to think about it?
I think that's a great point.
Okay.
Yeah. The imperfections of a scientific theory drive people nuts. We want theories to be perfect, but they're not. And that's where the science and the learning happens.
But what you don't know is whether the addition is just an add-on or whether you have to throw out everything and come up with a new idea.
Do you think that last gazillionth of a second will be explained, or is it even explainable?
We've got top people working on it right now. They're called string theorists.
Yeah.
Top people.
And
Cosmologists in general. Yeah.
Top people.
String theorists is just one group of promising paths. But all of cosmology is really about trying to get that last little tiny bit.
Chris Carlton on Facebook asks, why aren't we expanding with the universe if we are part of the universe?
I get asked that question a lot by my students.
And I'm going to add a coda to that. Will I ever break 6 foot?
Are you still growing? We're still
Well, I'm
the
hopefully still
machines
expanding.
That can help you there. We will get to the answer to that when we return for our second segment of Summer School, StarTalk. We're back in our second segment of StarTalk Summer School. When you have to go to summer school, you got to bring in the big guns. Charles Liu, Professor.
Thank you, Neil.
Professor Charles Liu, CUNY Staten Island. Matt Kirshen.
The little gun.
The little guns.
The littlest gun.
Wait, so how tall are you? How tall are you?
Like 5'5".
5'5" and 120 pounds.
Yep.
8.5 stone. Let's be specific.
Excuse me. 8.5 stone?
Yeah, because Britain really doesn't know what units to use. we're metric sometimes, and sometimes
Which
we're
stone? You know.
In some cases, we're ahead of you. We do fruit and veg in metric. We'll normally do Celsius for temperature, but then we'll do stones.
Yeah, you have issues. You have metric issues.
We're comparing things to the size of animals. It's
Oh, that's where the stones come from.
I don't even know.
No, that's
what
where the
a stone
hands. Well, you have
originally is,
hands.
but-
for the
hands
horses.
and yeah.
Whose hands? Whose feet? You know. So we left off at the first segment a question.
About yes, if the universe is expanding and we are part of the universe, why are we not expanding?
And the answer is electromagnetic forces. See, the expansion of the universe is its own thing, but it does not counteract on small scales. Things like atoms and molecules pulling one another, or electrons and protons, or even
Literally, the atoms
gravity.
and molecules in his pinky that he was pulling.
Right. So
As he picks his fingers on his hand.
that's
yes.
an excellent point. Yeah. So the reason my pinky nail is not expanding away from my pinky finger is because they're being held together by other kinds of forces
Way stronger forces
in the shorts.
in the short distance.
Yeah, in the short distances.
Yeah.
So out at the distances of millions or billions of light years, the expansion of the universe dominates. Even galaxies are carried along for the ride. But on scales of humans, or even planets, really, those other forces are much stronger.
Even the solar system is not expanding.
That's okay, because I've been given the analogy in the past of the blowing up the balloon and watching the dots get further
right.
apart.
On the surface.
That's right.
But is it then almost more like sort of blowing up a globe that has like ice sheets floating on it, but the ice sheets stay in one clump,
That is a correct, better
Yes.
assessment. To
and they
this.
become further apart as
Yes.
the globe expands.
Yeah, on a balloon, if you drew a galaxy on it, that galaxy would actually get bigger. Yeah, but
Right.
that's not
so
what
if you
happened.
put like little sticky notes on the balloon, then that would work.
Right,
Yeah.
sticky notes that have the ability to
Little
slide.
lifesavers, you glue them on, and they'll
Oh,
just
yeah.
stay in
Right.
one
Yeah, you
shape
can do
as
that
the
too.
thing goes in.
So the sticky notes themselves, or the lifesavers, would become further apart, but within themselves they
From
would
one
stay the
another.
same size.
Right,
Correct.
yeah, you got it.
Okay,
Yeah.
It's a very
I
good
understand
question.
something a lot better now.
There
We
you
got
go.
good question
We
people
do.
out
We
there.
do.
Man.
We have what an excellent audience.
This is
StarTalk
an
has.
excellent audience, unless they just called from.
No. I'm sure these are.
We'll check with our
run-of-the-mill.
researchers to find out. All right, Matt. Next.
All right, from Ben Ratner at Ben Makes TV on Twitter.
Oh, that guy.
I've heard of that guy
Oh,
before.
yeah.
Ben says, "Please describe the laws of physics." It sounds like we're doing Ben's homework.
Oh no! Here's what I'm doing. I'm going to pull rank here. You ready?
Go ahead.
Okay. In one of my books,
Yes.
I have a chapter called "Unearth as in the heavens.
Ooh.
And it's all about the effort to discover laws of physics on Earth and the question about whether they apply in places other than Earth. And it's not a given that that should be the case.
Okay.
It might have been that something you discover here on Earth is different on Mars or different on, but it turns out it's not. It's the same.
What I would be interested in is not necessarily the laws of physics, because that's what I live with all my life.
Do you?
Yes.
Do you have a
But-
choice?
What are the laws of psychics?
I don't understand.
Well, laws of physics, right?
Yeah.
Natural stuff, predictable, whatever. But the laws of psychics, like people who make predictions about the future, people who cast themselves as those who understand things that are beyond nature. What are the laws of psychics?
Maybe there are no laws.
Well, then why is there a major in psychic studies?
Not in any university I know of, unless it's in Arizona.
Astrology. Yeah,
Or-
I think it's in
Arizona
Arizona.
has
Yeah, like a
Yeah, other than Arizona, I don't think any accredited university has a major in astrology or psychics.
yeah.
Yeah.
But surely, if such a major does exist, then there must be some laws that they must follow.
Okay. I've never been curious about that. Maybe I
Really?
should be.
I don't know.
Yeah.
Maybe
Here's
we
the
can
thing.
get. Yeah, we can
okay.
get.
The headline you've never seen.
Yeah.
Psychic predicts winning lottery number a second time.
That's true. That's true.
You don't get that.
That's true. Well, we'll have to ask this questioner. Yes, what Ben Makes TV thinks about the laws of psychics.
Okay. But otherwise, the laws of physics are very simple.
Yeah.
I mean, they fit,
Okay.
I remember I was in school and somebody was taking an accounting class and I saw the book that they were carrying. It had like 1 million pages
Yep.
in the book.
Yep.
And my book, which was on like all of gravitational physics, had like a third that many pages. So I can understand the whole universe based on what's in my book, but they need a book 4 times as fat just to be able to do somebody's taxes.
Fair enough.
And I
And
said,
that's because you can't deduce the tax code.
you can't deduce it. Thank you. That's the difference.
Yeah.
The good thing about physics is you learn some rules and then all the rest derive from them.
Pretty much.
Very
yeah.
powerful.
When
And then
we-
every so often, someone comes along and goes, actually, those rules are all slightly wrong.
yeah. And
Well, we have Newton's F equals ma.
Right.
You got equals mc squared.
Yep.
You got Maxwell's equations.
Yep.
We're done.
pretty
Practically.
much. Yeah.
Throw in a few quantum physics equations.
Years
Schrodinger
worth
equation?
of physics. Yeah, years worth of physics study is just F on one side, force, and then ma, mass times acceleration, on the other side, and you just change F in a gazillion different ways. You change ma in a gazillion different ways, and that spring
And the
from
universe
that springs force the
unfolds
physics.
for free.
Yeah, absolutely.
Yeah, it's beautiful.
Absolutely.
It's beautiful.
Great question.
All right.
I really enjoy this question because, apart from anything else, it came from a 4-year-old.
Oh,
The 4-year-old
But you
son.
tell us after when we're stumped.
yeah.
The 4-year-old son of Pinti from Laos asks,
Laos. Ooh.
Nice.
why do punctured balloons fly around chaotically? Why doesn't it fly on a straight line?
Wonderful question. When you have a rocket, actually, you know how they travel in straight lines, and we're always very impressed, right? But what we don't see is the amount of control mechanisms and structures within the rocket that make sure the exhaust comes out in a very orderly and a very directional fashion, right? When you puncture a balloon, the exhaust that's coming out is coming out in a way that's poorly controlled. It's not a pinpricked hole, for example. There's a difference. You can try this. You put a little tiny hole in a balloon as opposed to a large hole in the balloon. The larger the hole, the more chaotic the flow goes. So it's a matter of whether or not you can control the air coming out in a reasonable or a linear way compared with whether it's just rushing out all at once.
Well, also, you'd want the movement of the air to line up with the center of mass of the balloon.
Yeah.
Okay.
Right. And
So if that lines up, then the balloon will just be pushed in one direction. If the jet's air is coming out at an angle different from straight to the center of mass, you'll start rotating the balloon. And
Right.
Plus, the balloon is not symmetric. There's that little, the bottom of it where you got the knot.
the knot.
The knot. So the balloon's weight is not symmetric.
And the center of the mass of the balloon would also move around as the balloon deflates.
Yes. Yes.
That's right.
So what you'd have to do is configure something, like get a straw maybe to guide the air a little better, have some stabilizers, and then you can make a balloon rocket.
Yeah. That would be a lot of fun.
But I love that question.
It's a great
That sounds like a kid that's tearing up birthday parties.
I want that kid on my research staff.
So,
by the way, most of the time when you pinprick a balloon, it blows up.
Right.
Right. So you have to do this carefully.
Yeah.
Right.
I learned as a child, if you put a piece of tape on the balloon, then you poke the hole through the tape, then the rubber or the outside like flexible stuff doesn't rupture in a rip, and you just get a little hole, then you can have it go around.
So you've done this before.
Of course, hasn't everybody?
Okay, no, I haven't put tape on a balloon to puncture it.
Oh, give it a try sometime.
But it's way more fun to just pop them.
It's too fast.
It is too fast.
It's too fast.
It's too fast.
Yeah.
You are correct. Okay. I will try this from now on. Any kind of masking tape or?
I used like plastic invisible tape.
Okay.
You know,
Scotch tape. Okay.
Yeah.
Good.
Priv on
Wait. Now you put on both sides of a balloon.
There you go. That's
then the balloon won't know where to go.
It won't know where to go.
Oh my God.
It'll start spinning. That would be fun. All right. 4-year-old balloon experiments.
Yeah, I like that. So Pulsar Priv on Instagram says, "Hi, quick question. How would you explain neutrinos to dumb teenagers who know nothing about astrophysics?"
Okay.
And the questioner doesn't make clear whether they themselves are the dumb teenager or are trying
It's
to...
a friend. I would explain to a friend.
Let me jump in right now and say that there are no dumb teenagers. There just aren't. I'm an educator, and maybe I'm showing my bias here, but I've never found an actual dumb teenager. They can pretend to be dumb. They may think they're dumb.
Cool.
Yeah, but they're not actually dumb. I want people always to feel like that they are smart because they are, and not have to act dumb or pretend to be dumb to be cool. All right. So there's no such thing as a dumb teenager. That's just my opinion. Sorry, had to get it out there. Now, to answer the question, a neutrino is just a little tiny particle that comes out so that in atomic interactions,
Nuclear interactions.
in nuclear interactions, energy is properly balanced. Okay, both in the motion and in the amount. I think that's really what a simple way of describing a neutrino is.
It's a pretty weird particle because no one knew they existed, and there was an imbalance in the experiments that were being done in nuclear physics. And it was Enrico Fermi who said, there's got to be a particle carrying away this momentum. There has to. We're looking. We don't find it. It's got to keep looking. It's got to be. What properties would it have? We can't have any charge. So it's got to be neutral. And it's got to be really low mass, little. So it's got to be little and neutral. And
well, the funny thing is,
and so in Italian, neutrino.
Right.
Like bambino, neutrino.
So it's just the diminutive version of neutral.
Of neutral or of a neutron. Right.
But the funny thing is, when this was first proposed, the neutron had not yet been discovered. So when the neutron was discovered, people were like, oh, is this it? And did more calculations.
No,
nope, still not it.
Yeah,
There's
too
something
massive.
That's even smaller than the neutron.
That has no charge.
That has no
Right.
charge.
So yeah, it's necessary to what's going on in the universe, but it's very hard to stop. It plows through anything.
Right.
What's the number of neutrinos that go through your thumb every second from the sun?
Many trillions.
Trillions.
Many trillions.
Can you feel it? Matt,
Can't
can you feel it?
I'm going to kind of bit. It could be the air conditioning. I don't know. It's hard to tell. So how do
Because they don't interact, and that's why they were so hard to detect.
right.
But they do interact very minimally, right? We can detect them.
And it was one of the great experiments in astrophysics that allowed us to find neutrinos coming out of the sun. What happened was that people took a very large vat of dry cleaning fluid, very pure, put it down more than a mile below the surface in South Dakota, and surrounded it.
I think it was just a pre-existing salt mine, wasn't it?
It was a gold mine.
Oh, gold mine.
A homestake gold mine.
Gold mine, not a
Right.
salt mine. Okay.
And it was sunk all the way down to the bottom. They put it there, and they surrounded it with a lot of cameras. And so they just watched this tank of very pure cleaning fluid. And when a neutrino hit, even though trillions and trillions pass through every second, they might only get one neutrino hit every once in a while. And when that happened, there would be a flash of light. And so they'd watch it and make sure that the flash of light is not caused by anything other than a solar neutrino. And that's what it was. So it was an
Why cleaning
amazing
fluid?
discovery. It turns out that particular molecule, perchlorate,
Yeah, but I think it needed the chlorine in it.
had a special nice property that it would, when hit by a neutrino, and with that interaction, very rare occasional interaction, would cause that flash of light to be detected.
How long ago did that experiment happen? Was it
A
recent?
couple of decades.
That
yeah.
was several decades ago.
It was still
70s.
Ray
80s.
Davis Jr.
Yeah.
was the experimentalist. John Bacall was the theorist that was
And Ray
involved
Davis
with
got
that.
the Nobel Prize, I
Yes,
think, for that,
that's
but
right.
not John Bacall. So
Yes, yes.
people didn't fully understand that. You have the theory and the experiment and the observations.
Mm-hmm.
They all have to come together to make that discovery.
That's correct. But that was a real triumph, and it led to a secondary discovery, actually, because it turned out that the number of neutrinos that were being detected from the sun were fewer than we expected. And so for a moment, people thought, wait a second, is the sun dead and we just don't know it yet? It was known as the solar neutrino problem, because those neutrinos had to be produced in order for nuclear fusion to be going on. So if they were half as many as we expected, then maybe the sun itself was starting to run out of fuel.
Scary prospect.
Yeah, scary prospect. Turned out, though, that it was just something happening in our upper atmosphere called neutrino oscillations. Another amazing discovery.
Yeah, so it'd be I throw you a basketball, but you catch a football.
Right.
So the experiment was designed to detect basketballs, but you were actually receiving footballs.
and what it is someone in between us is swapping them out.
That's right. And it was amazing. That was what was happening. Yeah, these neutrinos come in different flavors, it turns out.
Yeah.
Who knew?
Who knew at the time? Right?
Oh, okay. So there isn't just one neutrino particle. There's
3. Yeah,
okay.
3 different kinds. Electron neutrinos, tau neutrinos, and mu neutrinos.
And their antimatter counterparts.
And the antimatter
Really
counterparts.
6.
Yeah.
Yeah, it's pretty cool.
Physics is amazing, isn't it? I love summer school. Great question.
Summer school. Next question.
All right, Kyle Ryan Toth on Patreon asks, ignoring the cold, could a settlement survive on the surface of Pluto? What would radiation levels be like? Are there any useful resources other than water ice?
Hold me back. We'll get to that question when we return on StarTalk. Matt, before the break, you had a Pluto question.
It is, yeah.
You know, me and Pluto have history, but we buried the hatchet long ago.
Well, whether it's a planet or not, could a settlement survive on it?
Oh. Well, you can ask why would you want to do such a thing?
Right.
But just take, for example,
Yep.
Charles.
Yep.
Is there a line of people waiting to settle in Antarctica?
No.
And Antarctica is warmer and is balmier and wetter than Pluto.
And there's penguins. To the best of my knowledge, there are none.
And in a pinch, we can eat a penguin, right?
That's right.
So Pluto, in principle, Charles, in principle, we could just pitch tent anywhere. You just bring enough resources,
Yeah,
right?
yeah. The settlement could survive there as long as you could shield yourself from the cosmic rays that hit it, and as long as you can keep yourself warm, because the temperature is so low out at that distance.
Yeah, and food. You need no way to generate food.
You need food.
How faint is the sun? If I was standing on the surface of Pluto and staring straight at the sun, which I presume I would be safe to do,
The flux is only about 1/1600th the amount of flux that we get from the sun here on Earth.
Is
So
it
what would that
only
be?
that much? I thought, I'm going on a memory now, not on a calculation, that the sun from Pluto is about like a full moon night here. Is it
Let
brighter
me do that
than
quick
that?
calculation there. Absolute magnitude -26 for the sun,
And-
-15.
no,
for,
12.
Minus
Moon's
12
12,
for the
yeah.
moon. So that's 14 magnitudes.
14.
So that's a factor of 10.
So 7.
Yeah.
So 10 to the 4. That's 10 to the 14.
No, not quite that much.
Yeah. 7 magnitudes. Oh no, sorry, 5.
Yeah.
5. So it's a factor of 100,000.
Right. So it's a little bit.
And you said it's.
I said 1600 because it's a 40 AU, right?
Oh, you just divided
1/40
it
the
out.
distance,
yeah.
yeah.
Okay.
So
That's rated as per HuffPo, 1600.
1600. Yeah.
yeah. So there
There
may
may
be.
be HuffPo to find out if we're. You're in the middle of an active calculation here. You pull up a HuffPo page.
No. This actually brings up a very good point, and I teach this to all my students. And since this is a summer school episode, it's quite appropriate.
We are 40. Pluto is 40 times farther
Right.
away from the sun than Earth is on average, and so it's 1 over that square.
That's right. So that's where you get the 1600.
1/1600th as bright.
That's right. But the idea that a person
Inverse
can
square law of light. Very cool.
The idea that a person can just pull up the answer on Google faster than we can do the calculation brings up a really important point about school in general and education in specific. You might agree with this, Neil. We can no longer think that we are educated if all we can do is memorize facts or calculate things that can already be calculated and sit on a database. We have the world's information at our fingertips. The only way that we can remain viable as a productive member of society or as a civilization is if we are better than Google. We have to do that. And I'm just not picking Google specifically.
Sounds like he doesn't want to be replaced with a robot. Matt, does that sound like that to you?
It is absolutely right. We all can easily be replaced by a search engine. Our education system, our learning, our interaction with nature and with the world and with other people must be better than the search engine.
Well, we know
Charles
already
for
that
president. Charles for president.
we know that Charles is a better singer than Google, so
I think that was Charles's stump speech right there.
Yeah.
wasn't
Oh,
it?
dear.
Yeah.
while we are talking about singing and the like, Marcus, and I'm going to apologize for butchering this name, but Guimares, I apologize if that is way off, on Patreon asks, I had a debate with a friend of mine where he said that scientists hate arts in general. I think that's not true, says Marcus. Dr.
Excuse me
Tyson
while I
loves
go and
art and he
throw
loves The
up.
Starry Night by Van Gogh. Could you please tell us something about the subject? Charles, you okay there? You seem put out
Science
somehow.
hates art? No way.
Yeah,
no
I don't know.
way.
First, I don't know any scientist who hates art. A. B. Many scientists I know not only just don't hate it, but love it. Yeah. C. One of the books behind you on a shelf is called Mathematics and Art, a book written by an art curator who has fascinated by the role of science as it has influenced art. And I was privileged to be asked to write the foreword to that book. And as the writer knows, I'm a big fan of The Starry Night by Vincent van Gogh, 1889. And so And I'm not unusual in this regard. Our colleagues love music, love art, on levels that you might not even know or suspect. Because generally, if they're in the news, it's not because of that; it's because of the science they're doing. Oh no, we're art-loving community all the way back. And why do you think universities they're called the schools of arts and sciences? We go way back.
Yeah, way back.
Two sides of a coin, each the pinnacle of human creativity and expression. One constrained by the universe, the other constrained by imagination itself. Science and art.
I could not say it better, Neil. It is absolutely true. Science and art are inextricably intertwined. There is no scientist I know that doesn't like art.
Have him take up that question with Leonardo da Vinci.
Absolutely. And Albert Einstein himself wrote in 1930 that the sense of the mysterious, the wish to be awed by things we don't know, is the root of all great art and science. And I agree with that statement.
Trina Jennings on Facebook asks, if we can figure out the center of the Milky Way galaxy smells like raspberries, can we figure out what things would smell like elsewhere? Would the center of all galaxies smell like raspberries?
Who said the center of the galaxy smelled like
Oh,
raspberry?
it's a cute press release about people who are looking at molecules in gas
molecules.
clouds.
Okay.
And it turned out that they detected certain aromatic compounds which are found in raspberries.
Okay.
So they said, oh, it smells like raspberries. Oh, it smells like raspberries because there are these volatile organic compounds that are in gas clouds near the Milky Way galaxy center.
There's also a lot of ethanol there, too.
Yes.
You sound like
so
a
to smell,
drunkard.
yeah, it would smell like a brewery. Yeah, and
No, that'd be the
actually,
yeast. I think the yeast is the predominant smell
right.
in a brewery.
That's right.
A
So in a
distillery?
distillery, yeah.
There's a lot of organic molecules in
Right.
space. So
And there's even sunless tanning lotion too, DHA in molecules over there. So you can not only get a great suntan,
I've never
you
looked.
can also
I-
smell.
yeah. I didn't know such a thing existed.
Yeah, sorry.
Up in the hood, it's not it.
You guys aren't tanning much?
Yeah, the CVS doesn't have that on the front counter.
You gonna do the spray tan?
No, not in the hood. So it's a little deceptive to say that space smells like that.
Right.
Space smells like nothing, unless you put molecules where you're
Right.
sniffing, and there are molecules everywhere, and so there it is. Then you're smelling molecules in space
Right.
rather than space itself.
Right. So to answer that question constructively, the
Yeah.
answer is yes. As long as we can find the molecules that create certain smells in our brains through our noses in a location, we can tell you exactly what that
What that would
place will
smell like, precisely.
But there are a lot of particles out there, and they can smell like a lot of different things. Yeah.
Indeed.
Nice. Who wants a relativity question?
Bring it on.
Yeah.
Hussein Sajwani on Twitter says, I am still having a hard time understanding the concept of how if your twin is on Earth and you travel at almost the speed of light, you will not age as much as them or something like that. Can you really try to dumb it down or using analogies?
Again,
Charles,
before Neil says
No, I'm not saying anything. I'm out of this one. Go.
Please don't use the term dumb down. We are not dumbing things down. We are merely translating the concept into a language that everyone can understand.
In that case, can you smart it up?
That's right. Thank you, Matt. Okay, here's the basic point.
Smart it down.
Yeah.
Smart it down.
Time is experienced at different rates for people who are traveling at different rates of speed. That's a very, very complicated concept if you're trying to lock it into our idea in our regular time that a second is a second is a second. But the moment you acknowledge the possibility that time is a dimension, like length, width, and height, and you can move through it at different speeds, then the twin paradox that is described here or other paradoxes become not too difficult, because what you're doing is measuring time intervals, right? You're not measuring actually the amount of time at this very instant, but you're measuring the time from the time you experience 1 minute ago to the time you experience a minute from now. That person who is traveling at a different rate through time and space will simply experience a different interval.
And you'll both call it a minute.
Yeah.
But relative to each other, they're different lengths. So, yeah.
And you only realize that once you come back into contact with each other.
Correct. Yeah, that's right. That's right. And the way to know who will be younger, because both of them in motion will say that the other one is their opposite clock is ticking slower, is that your twin who went out had to slow down, turn around, and come back.
Right.
And that breaks the symmetry. It's called a paradox because if I see you traveling and your time is ticking more slowly and motion is relative and you see me, I'm actually standing still, but as far as you're concerned, you're standing still and I'm moving. You see my time ticking slowly. How is it that at the end of this exercise, one person is younger than the other?
Right. How do we not know, like, if,
Right.
the train is going past the platform rather than the platform is going past the train?
And the
It was one of the
answer is
great jokes against Einstein, who said, "Hey, Einstein, when does Grand Central Station arrive at the next train?" Everyone was trying to get their head around this
Right.
back
So
at the time.
so it's specifically the acceleration of the one twin
Yes.
who goes out
That
on the
breaks-
spaceship and goes out and then turns around and comes back.
that breaks the symmetry.
Right.
Is
of
that acceleration and then deceleration? Then?
Right.
Yeah, the whole thing, it's either positive or negative acceleration, but it's just, it wouldn't matter. It's an acceleration.
the
Right.
one that leaves and comes back, that's the one that is the thing that appears to be wrong.
So it's an uncomfortable concept because we don't experience that in everyday life.
That's right.
As our active senses do. It was not necessary to know this on the plains of the Serengeti. To avoid getting eaten by a lion, you didn't
Yep.
need to know relativity.
But it's absolutely necessary in this day and age of atomic energy and very, very high speeds.
Matt, it's time for lightning round.
Oh, yeah.
Okay.
Nice.
See if the bell works. It does. So Charles and I will try to answer in sound bites.
All right. Well, we're going to jump back from Einstein to Newton. DJ Milky on Instagram says, I read a few years back that the Earth is technically falling into the sun, but doesn't actually go into the sun. Is that true?
Yes, and the reason it doesn't go in is because it's traveling at orbital velocity around the sun.
Yeah, if we traveled any slower sideways, we would get closer to the sun. So we are falling towards the sun, but we're being held up, if you will, by our very high sideways speed. So yeah, we got this. And Isaac Newton first demonstrated this in Principia, and first drew it in the system of the world. That was his cliff notes for his Principia,
Terrific.
written in English. Very cool. All right, you got it.
All right. Code Monkey IA on Instagram says, what causes the Earth's magnetic poles to move, and what would cause the magnetic north and south to flip?
Very good question. Our magnetic field is created by the dynamic motion of ferromagnetic materials inside our Earth.
Iron.
Yeah, almost all iron.
It's almost entirely
Almost
iron.
all iron. And because of that, because it's fluid and it moves, that's why our poles move. It's as if you had a dancing magnet inside, but it's kind of somewhat semi-solid, somewhat liquid.
And it rotates, but not exactly the same rate that Earth does. So all these dynamics influence which direction on Earth's surface you find the North and South Pole, and whether the North is up or down relative to it. And history has shown that the poles have flipped multiple times in the past. Yeah. Next. Oh, by the way, if Earth cools completely and the core becomes solid. The magnetic field shuts off.
It's frozen. Yeah, it's done.
Good. Good.
All right.
Sorry, it wouldn't shut off the magnetic field. It just changed the movement of the magnetic field.
Right.
Good. Good. Okay.
Evan Howington on Facebook says, if the universe is infinite, then how could time exist other than the meaning we give it?
If the universe is infinite is the key point. We don't know necessarily yet that the universe is infinite.
He's saying if it's infinite, let's change the question. Suppose the universe had no beginning and no known end, is infinite in time and space. What does it even mean to have a calendar?
Great point.
What are you measuring?
Well,
is that kind of the paraphrase of that question?
I think so, yes.
That's a good way to put it.
Yeah.
And what we would be measuring in time is the various atomic processes going on in our bodies. And a clock, like the definition of a second, is just a way to macroscopically allow us to know whether we're getting older or whether we're not.
So you need vibrating, repeating phenomenon to measure time accurately at all. So in a universe where nothing repeats, there can be no measurement of time.
Well,
What do you think of that?
if you can measure the passage of time or define the passage of time as the expansion of the universe, then you don't have to have a vibration. You can just have the change that's going in a single direction from smaller to larger.
Okay.
You
So
could do
time
that.
then gets measured by size.
Yeah.
Size of things. Interesting. Okay.
Rather than repetition.
Matt, last question. Go for it.
All right, I'm going to go with this one then. Billy from Queens here, out of
Billy.
Hunter College.
Give me some Billy.
Hunter College, City University of New York. Oh, yeah.
Cosmically Curious on Instagram says, what are some tips for an everyday astrophysics student who wants to become an extremely successful science educator?
Read Neil's books. I don't know. I really love it when educators express their knowledge in the language of the people who are listening. In other words, a really good science educator is essentially a very good interpreter, a very good translator. Not someone that dumbs things down, not just someone that turns things into sound bites, but someone that can really take a concept that's sort of described by math and science and turned into English or French or whatever language that the person is fluent in. That is the mark of a true science educator, thinking about the audience and not necessarily about the source.
Ooh. I can't touch that. I can't touch that. Other than to add punctuation and say that Galileo, an academic fluent in Latin, when he decided to write about whether Earth was in the center of the known universe or it orbiting the sun, he wrote that in Italian, knowing that the common folk would be able to then embrace and appreciate the discoveries he was making. And so that was quite a striking fact. That's like Carl Sagan appearing on The Tonight Show.
Yeah.
You're crossing
Pivotal moment.
You're crossing boundaries there. And then he became a regular guest on The Tonight Show, coming to the people, where the people are.
Right. And never like claiming that he was somehow smarter or better than they were.
Empowering people to think even more highly of their own intellect that maybe they only just discovered for the first time.
Well said, sir.
We got to end it there. Charles.
Neil.
Dude. Love you, man.
Love you too, man.
Family, everybody's okay?
Everybody's good last I checked.
Excellent.
right.
Matt.
It's been a joy.
When you come back, can you weigh like 10 pounds more or something?
All right, I'll put
Make us
stones in my
all feel a
pocket or
little
something.
Growing taller, we don't expect that, but there's a gym somewhere. You can put on some...
I'll stretch myself out. See if I can weaken those electromagnetic bonds that you were talking about.
There you go.
Do I rub magnets on myself?
Yeah, and I'll stretch them out, and then you'll get it. But Matt, always good to have you.
It's always good to be here. Thank you.
Probably Science is going strong.
That is the podcast.
We look
please
for
check
that
it out.
on the podcast. You've been listening to and possibly even watching this episode of StarTalk, our edition called Summer School. I've been your host, Neil deGrasse Tyson, and as always, I bid you to keep looking up.